Okay, thank you for bearing with us. We are only a few minutes late, but we're the last session. Thank you for hanging around to come and talk video games with me. Yay! Woohoo! I haven't got time to take pictures now, but if you don't all scarper at the end, I can get my usual selfie with you all, and, you know, I like to do that. So we'll see you at the end, okay? Warning, flashing lights, a bit of bad language, and video game violence. Woohoo. All right, I'm going to go stand over here, or else I'm going to be like around the place, and I'll get too distracted. So we are talking the forgotten AI of video games. Thank you very much to our keynoter, Jodie, for setting me up beautifully this morning. So hopefully you're all experts on some of the things we're going to talk about today. All right, so let's go and think about what AI in video games means, okay? There's quite a few aspects of it, and we're going to be focusing on one particular area. But first, AI as part of the game. So I'm thinking your NPCs, your pathfinder, things that affect the way you play the game and how you interact with the game, the actual gameplay bit of it, okay? So let's have a look at some of that. This is from Skyrim, no, Oblivion.
Guards, we've got a pickpocket here.
Bit dodgy AI, because it's Oblivion.
Little thief, how dare you touch me?
Pickpocket! Treacherous little pickpocket! How dare you steal from me?
So their AI is going a little bit haywire, but it is Oblivion. It is well known for dodgy NPC stuff. So that is where you have AI as part of the gameplay in a very charming way. We also have games such as one of my personal favorites, RimWorld, where you have AI that has automation through it, simulation, okay? So we can see here in RimWorld, you as the player build the sort of environments, the buildings, and then the simulation runs. It was a bespoke AI in this, built by one man, so it's very... if you've ever played Skyrim, I've got Skyrim on the brain, RimWorld, you know, as you get more and more in there, it gets slower and slower and slower. That's quite common with quite a few games, okay? So that's the first type. The second is AI as the content creator. So that is more new, okay? The other type of AI has been around for a very long time, as we'll be exploring. So this is things like procedural content generation, for better or worse, in Bethesda's Starfield, biggest disappointment of the decade. That, I couldn't even get very far in it. We also have MP speech in games such as Fortnite, where you can provoke Darth Vader into swearing, okay? If you saw that, I don't know, like earlier on in the year, Fortnite put in where you can talk to like actually verbally talk, and after a few moments of thinking, an NPC, a non-player character, will respond to you. Okay, so that was that. And I use this. This is my game, The Third Tourist, and we actually use it to generate the speech. So if we come in here, we'll hear the audio.
This place is huge. I'd better not get lost. I should take a look around.
Completely AI-generated voice and text-to-speech, okay? As a two-person game, that's really useful for us because voice actors, amazing as they are outside an indie game studio's budget, okay? So thank you for that. So that's another way that you can use it. And then the final way, which is really awesome, is modeling player behavior. So this is the matchmaking, so getting like-leveled players into the same match, so you feel like you're not being annihilated by the people you're playing in PvP, player versus player, cheat detection, and sort of moderation and analytics. So I think League of Legends use AI extensively to identify and penalize toxic behavior. So people just generally being dicks to each other, okay? It cuts that out. So it makes the playing environment much better, okay? However, we're not really going to talk about that. We're not talking machine learning. neural networks, graphics AIs, or generative AI. Graphics AI is really interesting as well. That's things like DLSS, that's deep learning super sampling from NVIDIA. There are other versions of it as well. And that's taking your output of your game from the game itself at a lower resolution, so let's say 1080p, and it upsamples it so that you have 4K, for example, but less tax on your CPU, all right? So it can do that in your GPU. So you can get better graphics with lesser hardware, all right? So that's what that does. It's very cool. But we're not talking about that, all right? We are going to stick with AI as part of the player experience, but not generative AI like I showed you for my game, okay? So to understand how we get to that point, though, we need to go back in time a little bit. We're not really going to go down the rabbit hole. Jody did that this morning. All right, so we are going to just have a little look at where this AI originates from. So I actually stole this graph from another talk of Jody's. We're just like cannibalizing each other's talks. It's great. So this is narrow AI classification. That's where we look at AIs that do quite particular specific jobs. They're not broad, like wide-ranging general AI like ChatGPT. They do very specific things like folding proteins. It's very specific, okay? But if you look all the way over here, we have this thing just above, a calculator called emerging narrow AI, or sometimes known as good old-fashioned AI. That's what we're interested in, that little tiny sector there right at the beginning. So, as said, that's good old-fashioned AI, logic-based AI, classical AI, or as you all learned this morning, symbolic AI. All right, so we're going to be calling it symbolic AI, because that's kind of its proper name. So what is it? Well, we're going to go back in time to that first AI summer of 1948 to 1966. And we're going to use GPS to find our way there. Not really. It's not that GPS. We are talking about the general problem solver, okay? So this came out in 1957, and it was, I'm going to read these off, Herbert A. Simon, J.C. Shaw, and Alan Newell worked on this at the Rand Corporation and Carnegie Mellon University. So they were building on their earlier work of sort of artificial intelligence and cognitive psychology, and they came up with this idea, and it was part of their broader research into human problem solving and heuristics. I never get that right. Heuristics? That, okay? So, what is a symbol? Well, let's take it really basic. All of these are symbols. Okay, we have the man, sunglasses, clouds, trophy, star, Game Boy, everything there is a symbol. We're very good at classifying things like symbols as humans. Now, these symbols have a relationship. This man has a relationship with sunglasses, okay, because if he's got those on, he's cool, okay? So, what does that look like when we start getting into the nitty-gritty? Well, it's just some maths. We have false is 0, true is not 0, that's a good one, isn't it? And is multiplication, and or is addition. So pretty basic stuff that they were using. So if we have the idea that, is the kid wearing a cool old hat, and we're asking our general problem solver, is this true? When we come in and put all the values in, we can see that only if they've got a cool hat, and it's an old hat, and the kid is wearing said hat, is the kid wearing a cool and old hat, okay? And everything else is false. Now, if it's wearing the child, is wearing an old or a cool hat, again, pretty logical here, either both and or basically, and if it's not wearing, the child is not wearing a hat at all, it is false. So it's pretty straightforward. So that's one of its biggest limitations. It really struggled with complex real-world problems. And it really required formal representations of everything. So you would have to be like, this is a symbol, okay? It couldn't really determine that. You had to go in and do that, obviously. It's a maths machine. It's basically a calculator. Remember, it was one up from the calculator? All right. We also had expert systems. Now, these are AI programs that simulate human expertise. So you heard about the medical one, Mycin, this morning, and a few others. These were developed in the 70s and 80s, so more the second AI summer. And they were the first practical usages of AI. Everything else was very theoretical and men in universities going through it. But this is much more practical. You required a knowledge base and an inference engine. But how did you make that knowledge base, okay? So we have that knowledge base, which people had to populate. And it was really labor intensive. So it wasn't kind of like, you just load in a whole load of data. People had to input this data. It wasn't very easy to use. But that's where you stored all your facts and expertise. Now, we had the inference engine, which is basically if this, then that. All right? That's what it did. But these had a lack of common sense. Even though they're called expert systems, they weren't very, expert, really. They were just doing if this, then that, okay? They were just little trees following things. And they're really not adaptable. They were very, very narrow. Okay. Now, you may be thinking, it's a calculator. This isn't intelligent enough to be called AI by the standards we have today with all these, protein folders and ChatGPT. It is still AI. That you cannot argue with. It is still AI. All right. So what is the influence of these systems that I've spoken about on video game AI? So the general problem solver inspired AI planners and search algorithms such as the A-star pathfinding and HTN planning. Don't worry, we'll go into those in a bit. And then the expert systems led to rule-based AI, such as behavior trees and GOAP, goal-oriented action planning. Okay, and then there's a big difference with video game AI, and I really like this quote from Sergio Barriales, and that is, in a video game, our number one goal is to create a fun and rich experience. Our objective is not to build a perfect simulation, nor it is to always find the optimal solution to our problems. We are crafting an enjoyable experience, an apparent artificial intelligence, an illusion. That last bit doesn't sound too dissimilar to today, but, we'll move on. So, what are our core techniques? So, the very first one that we're going to look at is the finite state machine. It's the sort of earliest, most basic type of AI you can have in a game, I think. There's probably something more basic, but we're going to go with that being the most basic. So we'll call that an FSM, a finite state machine. And then, who gets chills from that? Yeah? Especially with all that bass. Yeah, okay. If you are unfamiliar with what that sound represents, it means you are about to play a frickin' awesome video game called Half-Life. And that is one of the earliest games to really embrace AI and have a finite state machine, okay? It came out in 1998. It wasn't the very first one to include AI, but it was one of the most defining games. So it used a finite state machine for all of its NPCs, known as monsters, and even the friendly ones, or the scientists, were labeled as monsters, and they went through all of these states to make it feel immersive and really cool, okay? So, what is a finite state machine? It's an AI where an AI character, so that NPC, that non-player character, or an agent, we still call them agents as well, transitions between predefined states based on inputs or conditions. Now, this came about first was spoken about in a paper from 1955, in that first AI summer from George H. Mealy, and that was a method for synthesizing sequential circuits. And then again in 1956 by Edward F. Moore, Gedanken experiments on sequential machines. I mean, these titles were so catchy, but they were talking about finite state machines. Now, what does that look like in a video game? You see Pac-Man there? Yeah, FSM. All right. Now, if you play any game where you control a character, you are using an FSM, because any sort of those animation states go through a finite state machine. So here you can see we have fall, idle, jump, and run. They all go through. You can transition between those states. And that is a very simple FSM. Now, if you need more complexity than that simple thing, you're going to have to go to a hierarchical FSM, because they get really complicated really quickly, and managing all those states and the transitions between them is not for the faint of heart. So what is a hierarchical one? Well, it has like sub-FSMs. It's like nested finite state machines, and that looks like this. So here you can see the outer FSM, the top level one, is idle, duties, combat, and wonder, and we can transition between those 4 states. But once we're in either combat or duties, we can go through further states. So we have in the combat getting cover, ranged attack, rearm, melee attack, and so on in the duties. And we can transition between any of these at any time, depending on external conditions. And now you can see already that looks like a big old tangle that you wouldn't really want to be maintaining. So when you're getting to this state, you want to move on to behavior trees, which is our next type of AI. So this is a directed acyclic graph, and it's a collection of nodes that are connected. It's a fixed direction. Whereas the finite state machine could go everywhere, a behavior tree starts at the top and works its way down depending on those external inputs, and then goes, oh, okay, I can do this because of that, all right? So we can see how it's getting that if this, then that from those expert systems. So it has lots of nodes, and those are all different types, such as selectors, sequences, and decorators, and this is an example of a behavior tree. We always have the root, and then a sequence. If we come down to that one on the left, it would be for the left for you, I had to think about that, and then all the nodes that don't have child nodes are considered leaves. Leaves, I don't know, leaves. We'll go with that. So all of those are at the bottom of the tree. A sequence will go through all of those leaves. A selector will pick between the two. And then if we have a closer look at we see that the sequence is AND. We've got all those ANDs. Traditionally, it evaluates from left to right. And if any of those nodes in a sequence, if any of those nodes as it passes from left to right fails, the whole sequence fails. Everything has to pass. Now the selector, as you can probably guess, if the first child on the left fails, it goes and looks at the next child to see if that passes. If every child node fails, then the whole path fails, okay? Now I say left from right, but you can randomize them as well. Yay! Let's throw in extra rules. So some of those decorators, what we had if we go back and have a look at the decorators here, so you can see on the right, under selector, we had a leaf, and then we had a decorator. So what exactly does that look like? Well, we can have these overrides. We have an inverter, so basically if it's true, it makes it false. If you want it to always be true, you can have a succeeder. If you want it to repeat for a time, a while loop, and then you can have a repeat until it fails, okay? So now you start to see, oh, okay, I can see how I can build some interesting character behavior with that. Now, if you wanted to look at leaves, okay, and what that code might look like, remember a leaf has no children, it contains an action. So this is kind of pseudocode. We'll look at proper code in a second. And you can see we have some conditions, such as a time limit, and we have a state, like has it reached the destination, and then we can go through. So we kick it off, and then we gradually reduce the time. If they reach the destination before time runs out, it's success. Otherwise, if they run out of time, it's a failure, and if neither of those things, we continue and loop again. Now, I know that's quite small, but it gives you an idea of how that gets quite complex. So on the left is how we define like the node state, and then we go through all of those nodes, and then we have a tree structure here. So this is for a tourist in the game, and we give them lots of values here. It's all in C# because I write in Unity, and then we set up the tree, and in this case, they only have one task, and that is to wander. So you would add multiple tasks in here to give them that behavior tree. And it goes in order. The top task is the one that is most important. Okay, so if you wanted them to flee from a threat, you would put that above the wander task. Okay, so you put them in order of importance. Now, a little sidetrack is that if you look into game dev, you might hear things called blackboards. They're basically in-memory data stores for the state of the game, not the state of the NPC so much, although you can use them for that. They are generally like the state of the world, all right? So all of these AIs will be looking at the blackboard for their conditions and the world state, okay? So, behavior tree versus FSM. I think you can see how one is cyclic and more simple, and behavior trees have more structure, more order, and can give you more complex behaviors, up until a point. And then behavior trees become really complex, really difficult to maintain. You can see they're very tightly coupled, and that's not great as your sort of actions grow. If you want lots of emergent behavior, if you're into like immersive sims, which I really am, you're not going to get this sort of emergent reaction, human-like behavior from either of these. So how do we start getting more human-like behavior from our AIs? Well, to do that, we need to use advanced decision-making techniques. Whew, it is hot up here. Okay, now first though, we are going to have a segue to NavMeshes. Oh my God, I'm going to sneeze now because I looked at the lights. I looked at the lights. It's the end of the day, folks. Okay, so it's not strictly AI, but it's a very interesting algorithm. So what is a NavMesh? This is a NavMesh. You can see here this blue thing, okay? When you see your NPCs walking around a world, they're not actually walking on the same world as your player character. They are walking on a NavMesh. You can see here in this area, it's layered like floors. That's because normally when the game is running, there are buildings there. So a character doesn't need any of the geometry that you have in your game to move about. They have this thing called a NavMesh. So what is a NavMesh? How is it made? So there are three sort of predecessors to the modern NavMesh. The first one is the Voronoi diagrams, and this came around in 1950s to 70s, and it was named after the Russian mathematician Georgy Voronoi. Oh, I've got a typo there. Oh, shouldn't have said that. There's no typo. Forget that. Who defined and studied the general n-dimensional case in 1908. Now, if you look at this, it's very pretty. I always think it looks like plant cells or your cheek cells that you did at school. But each of those nuclei in the middle, if you draw a line between any of those, so let's take that one there and that one. So you use a Euclidean distance, a straight line, and you can see that the border between those is halfway. Every border here is halfway between a pair of nuclei. Okay, so you can see that's kind of how it worked, and it was very useful for path planning in robotics and video games. So a lot of this crosses over to robotics. The second way was meadow mapping in the 1980s, developed by Ronald C. Arkin, and this was to help robots navigate around the area. Okay. Now, what is vitally important here is that each of these shapes with the dotted lines, so you can see that the solid lines is the actual layout, and the dotted lines are the dividers that they made, and that's because all of the shapes needed to be convex. That means all corners are internal. Does that make sense? So you don't have any angles that dip in, like a star shape is not convex, because if you tried to go across, you would cross the boundaries. So they are all convex polygons. And then the third one is Quake's area awareness system. So obviously developed for Quake. This one is where you have all of these convex polygons, and then you have portals, and that's the doorways, and you can see that your agent travels between all of those portals in straight lines to get to the target. So you can see that we've got these 3 different techniques, all variations on a theme, and those all came together to make the modern NavMesh systems. Predominantly, the Voronoi and the area awareness system came in, and those are the techniques that are used today. Now, if we have a closer look at a NavMesh, so this is on the mansion you saw in the game at the beginning, so we can dig down closer and closer. You can see there how it's layered when we take the geometry away. And if we zoom in on the stairs here, you can see how it's divided up into those convex polygons, okay? So we're still doing that even today. And then our agents navigate between all of those polygons, okay? And what that ends up looking like is the agents move along like so. Now, you see it's mostly blue, but there are these pink areas. So those are desirable areas. So if you've played Grand Theft Auto, you notice how all of the characters walk on the pavements and the cars drive on the roads. That's because you have given higher priority to certain paths. And you can also see here the path, if I can highlight it, it's very faint. You can see the path that they're drawing, and it's a whole load of straight lines across points, okay? Right. So how does the NPC navigate the NavMesh? Well, that is via an A-star algorithm. So we mentioned that again this morning. And this is difficult to describe very quickly, and I've got a lot to get through, but I've got a whole load of resources at the end with videos to really excellent explanations of it. So you need to know a couple of things when you are planning. Now, the black is a barrier. You can't go through the barrier. However, you still need to count the squares, in this case, to get the distance from the start. Now, that is known as your G cost. Now, if we take our start, I'm going to point the start here. If we go up, left, right, or down, we count it as 10. If we go on a diagonal, we count it as a cost of 14, okay? Just because that's basic Pythagoras, okay? But we scale it up for ease. So let's see, how could we get to the end from the start? Well, we could go up 1 for 10, up another 1 for 20, and then diagonally across. So this would be 34, okay? We could also come up. We could go to here, 20. We could go across. We could come up to here, 10, diagonally across for 14 that way to add up to 24, and again, 10 up for 34. So those two routes have the same cost. Okay, so we also need to know the distance. So you can see there's a path that we could take. That would be a cheap path. Now, the distance from the end, the H cost, is very similar. We just kind of work it backwards, okay? It comes backwards. Now I'm starting to add in these ones around here because obviously we can't cross the black, so we're going to work our way round. So you've got that. That's your H cost for heuristics. One day I will get it right. And you can see there's a path there, how we get to those points, if we're looking at 38. And all of that comes together. So if we look here, this is each grid. We have our G cost and our H cost, and we add those together to get our F cost, the final cost. So when we're looking at this map, we would go to the top right from the start for 42, across for 62, diagonally for 82, diagonally still 82, and across, and there you go. We've got the cheapest route to them. And that's how that A-star programming goes. But we don't start with there because 10 up is the cheapest to start with. But that, you'll see that's red. Now that's because we've evaluated that. We go up, it's 10, but we can't go any further. We'd have to go to the right, and that would be 24. But 14 is less than 24. Okay, you see the top left? The top, not anything there. You don't see anything there because I said it. So we come up, and these ones are null, because if we tried to go up to this one, it'd be 14, and we'd have to go across to the right, and then keep going here anyway. So they would be more expensive. This one's more expensive, and we basically go through them, and as we iterate over them, the ones that are more expensive go into the closed pile. They are already evaluated. Green, we haven't evaluated, and blue is accepted. Now, let's come down here. This one, we go across to the left, and you'll see that these ones are really high. That's because we've sort of gone down and across and things like that. So you start, when you actually see this animated, you will see it just go out like a tidal wave as it evaluates every single node. This makes it look like it just knows how to do that blue path really quickly. It doesn't. So I encourage you to go watch the video link I share for Sebastian Laig's YouTube video on it. He explains it so amazingly. So if you want to have a look at that, go watch that video. It's like 20 minutes of your life, all right? So now that we've got that out of the way, we're going to look at some high-level systems. And this is where we start to get into the nitty-gritty algorithms. And the first one is goal-oriented action planning. This sucked away about 10 months of my life last year trying to make GOAP work. Okay, that's the acronym, not to be confused with GOAT. It is not the GOAT, it's GOAP. Now, this was made famous by the game Fear, okay? And this is really interesting. You can get the source code for Fear. It's quite an old game now. And their lead AI developer, he wasn't an AI developer when he joined. He was, I think, a level designer or something. And they said, you are going to design the AI for us. And he was like, okay. So the story is, he tells it, is he locked himself away for months to try and figure this out. He had no clue. It's one of those, I'm on it. I'm like, no idea. So he went and looked at the Stanford Research Institute problem solver, STRIPS. It's a bit more of a catchy name. And he went and looked at that. Now, that uses an initial state, a goal with an expected outcome or an effect, and then a set of actions. Now, each action comes with a precondition. We've been learning about preconditions, things that allow you to go and do something, and then a postcondition. That's the outcome from it, okay? So, all right, that sounds like everything we've already looked at. So, what's an example of a goal and an action? Quite often you need to reduce the hunger of your character. Now, we have some possible ways in which we can do that. We can eat raw vegetables. We can cook dinner. We can buy a takeaway. There's another typo I knew. You know when I said I had typos in my talk? It was this talk, not my workshop. I was going, I know there's typos here somewhere. It was here. Okay, so we have preconditions. These are the things that we can do. Do we have these are the things that influence our decision. Do we have a cooking facility available? Because if we don't, how are we going to cook dinner? Do we have any money? Because if we don't have money, we can't buy takeaway. And if we're really close to death, we should just eat the raw vegetables, okay? So these are things that we start to look at. Now, each of these actions will have different heuristics. Okay, so a vegetable may only give you 10 food points, whereas a cooked dinner may give you 100, and a takeaway might give you 200 or something like that. But if you eat the raw vegetable, you're not going to die, and then you can do other things. So that's how it starts to make decisions. Now, in fear, they had very few goals: guard, kill enemy, dodge, cover, and ambush. And then the actions to satisfy those goals were idle, attack, dodge, shuffle, dodge, roll, attack, melee, go to node, attack from cover, dodge covered, blind fire from cover. But we're going to watch a video now of someone analyzing the AI, okay? Because you can see how all of these things come together to make really emergent, human-like actions. So, let's watch. They pulled down a cabinet to make cover. I mean, that's what a human would do. You'd hide behind things. You'd pull things out to obstruct it. So you can see they're detecting flashlights. The one lone guy on his own is like, please don't find me. Please don't find me, okay? So it's really starting to become emergent and human-like. And that's one of the things it does. So you can see it's unpredictable. You don't know what they're going to do. You're focused here and another one's flanked you. And then you're focusing here and they flank you again. It's very complex, multiple steps. They're flanking you. They're throwing grenades. Another one's coming. So there's teamwork going on here. And it's really real. They're context aware. That's because they knew that they could knock down that cabinet. So those are things like nodes. We saw the move to node. Now, when they did this, they marked everywhere with this is a node, this is a thing. So when they came up with the action to go and get cover, they moved to the node and did that, okay? So it was really great. There are some great analyses of fear on YouTube, hundreds of them. I recommend, I've put some in the resources, okay? So it's fascinating to go and see how it's analyzed, and you can get the source code. So you may think, well, that sounds like behavior trees, but it's not. It's much more dynamic. It's decoupled. You can easily add more and more actions without having to go in and edit it. It's very open-close, which makes my web developer, me, and pattern person very happy, okay? So let's start. We're going to go through how we explain it, how it works. I'm going to explain how it works. And the best way is often dominoes, okay? We have a condition, number 3, that is our number. And we have a goal to get to number 7. And we have all of these different dominoes in the pot. So how can we get to number 7? So if we look at the top row, we can go to 3. 5 doesn't satisfy our goal, but we have another 5. 2 doesn't satisfy our goal, but we have 2 and 7. So that whole pathway gets us from 3 to 7. And you can see the next row, we just needed 2 dominoes to get to our goal, and the last one was a really perfect goal, okay? So you can start to see how heuristics could come into play with that, all right? So that's all very good, but how does it really work? So it's a 2-step thing. The very first one which isn't actually part of GOAP, is the goal selection. So the GOAP is goal-oriented action planning, but it does nothing to select the goal. So once you've selected a goal, and we do that by ordering them in list of priority, and then comparing the current goal with the potential highest priority goal, and whichever has the highest priority is then planned. So we come over onto this right-hand side, and we start the action planning. If the action planning returns a goal, we have returns an action plan, we have a new goal, and we can execute that action plan. So, excuse me, what does the action plan look like? Excuse me. Okay, so we've got that goal, and there are a lot of actions that would satisfy that goal. So if we start looking here, we've got the actions and the goal. And then we have effects. So that's the outcome. That would be our 7, or get into cover, okay? So when we take our first action, we look at the conditions for it to run. Does it have a target? And then the effects. And then we check, can it run? Because are those conditions for it to run met? So we look at that. Yeah, okay, so we've got money, and then we look at the states. Okay, so we've got the conditions, they're met. It's cloudy and we have cash. And then we look at the next thing, can it run? Because does it have a target? So that's the NavMesh bit. Not the NavMesh bit, but the target, can it navigate to it? If that's yes, then that action can run, okay? And if we get to this point, where we have multiple actions, so this is different from behavior trees, only successful nodes can be called leaf. So we can see here that we come down here, this end node here is successful. It will satisfy our goal, so that becomes a leaf. And we have another one over here. This one, still a node, doesn't, okay? So in this case, we now have 2 possible actions that will satisfy it. Now, you're thinking, well, that's right at the end, and that's quite key, and we'll come around to that in a minute. It's looking at the end there. And then once we've got those action plans, good old heuristics come into it again. We add them all up. Looks very similar to that A-star algorithm, doesn't it? And we get the cheapest. And that's because it is an A-star algorithm, okay? So remember how we got all of these here? How does that look when we are in GOAP? So much the same as when we're pathfinding. Up here, we have our open node. It's not been evaluated yet. We look, can it run? No, we close it. Yes, let's go and continue our evaluation. Will it be satisfied? So think of the row of 3 dominoes. The first one didn't satisfy our goal, but it had a child pathway, okay? So then we come through, get the new node, and we do a lot of recursion, and we keep going all the way through this, okay? And then if we get an accepted one, that is now that leaf at the end, okay? So we go through, we evaluate all the actions to try and get successful pathways down to our goal as the end condition, okay? So I think you can see that point 3 there can be very expensive to run, is quite the thing. You think about all those goals, all those, if you had like 20 actions, it's going to recurse through all of those. And this is a very heavyweight recursive algorithm in this state. You can do it in other ways if it gets too big, because you can really screw up your system, but mostly you do it through recursion, so it can be expensive. But this leads to unpredictability, because it's always looking at changing environmental factors in the master world state to see what can and can't run. However, it is very difficult to design the player's interaction because it's so random and amazing. Now, there is a well-documented game called War of Cybertron, which used GOAP. The sequel to War of Cybertron, and this is from High Moon Studios, if you want to look it up, is Transformers Fall of Cybertron. They were like, we're not using GOAP because the level designers were skipping the GOAP at the end for boss fights and using behavior trees because they could not get the player experience that they wanted. So they were like, no, we can't do it. So they moved over to a new technique known as hierarchical task networks. And I followed suit because I was like, this GOAP thing, doing my head in. So I then did a spike into hierarchical task networks, and I was like, yes, finally, my NPCs are doing what I want them to do. So this is structured problem decomposition. Okay, it's much more structure than GOAP. We put the domain knowledge into the planning. We still have goal-oriented flexibility, so it can be quite adaptive, but it's a little bit more predictable. We also can roll back the simulation because we make copies of things, and it allows you to design the narrative a little bit more. So when you're doing more of a narrative-driven story, this is going to help a lot more. It's also quite efficient because it doesn't do everything. It will just do the first one that it gets to. And if that satisfies the goal, it's like, hey, here you go, and off you go. So you don't have to do all this deep recursion. So how does this one work? All right, so it evaluates all the possibilities, and as I said, it can return just the very first one, and it can do partial plans as well. So it can get so far, reevaluate state, and either continue or get a new pathway. So each task in the network can be broken down into smaller tasks or subtasks, allowing for a more structured and detailed approach to the planning. And it moves down through the hierarchy, much like a behavior tree, and higher priorities on the left are planned first. And then we break them into less complex tasks so we can get them more atomic, basically, and easier to understand. So if we look at this is from a paper that I've shared the link to. It's actually from a site called Game AI Pro, and they have lots of white papers on game AI. I've shared all the links, don't worry. And they did a run-through of a little scenario called Trunk Thumper, and it's about a troll who uproots trees and thumps you over the head with them. So if we have a look here, also this is known as a depth first search algorithm. Oh, God, no. Got that right. Breathe. Depth first search, but it's also decomposition-based search algorithm. There we go. There's so many names for the same thing in all of this. So let's go and look at it. We want to be a tree thumper. Yay. So starting on the left, we check, do we have an enemy? Okay. If we do, we go on. Do we have the enemy within melee range? Okay, we'll go on, yes. So now we have attack. So that is one of our high-level tasks. And in here, we can do a trunk slam, or if we don't have a tree, we can go and get a tree. But then we have to navigate to the tree, pull up the tree, blah-de-blah-de-blah. So you can see we're now getting that context inside our planning. If we're not in melee range, we'll navigate to them. If we are navigating, we'll just hold the tree up or guard our face so we can't be attacked by arrows. And the fallback, which will always run, that's why it's set to true, is idle. We'll stand around doing sweet F all if there is no enemy around, okay? So looking at this is that depth first search. We have the root at the top, so it's looking a little bit GOAPy, isn't it? Now, the first thing we do is it a primitive task? And that means, is it one of those blue ones? Okay. Now, if it's a blue one, we go and evaluate that, and it will return true, okay, if it can run, all right? Now, the important thing you note here is the world state copy. When we plan with HTN, we take a copy of the world state and then evaluate based on that. And we change the values in that copy so that we can forward plan. Now, that is quite different from GOAP, which just looked at what is the end value that we want. Can we satisfy that condition right now? And then worked its way up. But this looks at, if I do this first thing in the pathway, how will that affect the world state copy? So if it's like, I get 10 coins by doing this action, your money will go up by 10 coins, which might allow you to do the next thing, which is buy food, because now you have, rather than 0 coins, you've got 10 coins. And it updates that as it goes along, so it can predict what's happening. Now, if you get to the end of that path and it doesn't satisfy your goal, it returns false, it can't run, that all gets thrown away. You haven't changed the state, okay? So that's why it's considered quite forward planning and has that rollback, and it simulates things. But it only does it until it gets down to, oh, wrong button, down to this return true. And then you don't have to keep recursing through all the other states once you've got a success. So it is less expensive to run. It's still pretty expensive, but it's less. Okay, so GOAP versus HTN. GOAP is backward planning, so it looks at the goal and works its way back. And so if you remember, once we got down to that leaf at the end, and we're like, yes, this one here satisfies it, we then get that, we're choosing this thing, and then we had to parse back up through the whole tree to get the action plan. So we're going back, we've gone down, now we're going back up, we're reversing them, we're making lists and collections in code, and it gets very intensive, okay? I have a lot more frames per second now I'm not using GOAP. Yay. All right. So it starts, it goes to the end and works backwards. It's a flat structure. It evaluates every possibility, okay? That's great if you want real immersion and human-like behavior, but not great if you want kind of, I'd like you to do this over that. And it has this focus on goal satisfaction. HTN, on the other hand, is that forward planning that I said. So it decomposes those higher level goals and subtasks and goes in sequence. It's got that hierarchical structure like the behavior tree, so it's a little bit more predictable. And it focuses on the task decomposition rather than the goal satisfaction. So that's what allows it to be more context sensitive. Now, when you're choosing one over the other, there's a whole load of factors. So I'm not going to go into that. One of them is, I've already said, is getting your NPCs to do what you want them to do is really difficult. So we're now going to go and look at the final sort of level of AI systems, and that's complementary AI systems. Not every game has these, but a lot of them do. And these work in combination with all the other AIs to give you even better gameplay. So the first one we're going to look at is Director AI. This one manages the pacing and the flow of the game to enhance the player experience. So it's not really looking at the NPCs, it's looking at the big picture. It is a director. It will orchestrate the AIs. It's like, I think you lot should go over there. And it's kind of like that. And in the case of Far Cry, it's like, you lot are 250 meters away from the player. You're all going to be deleted off the face of the earth, okay? So it does that for performance. It starts culling things that aren't there. It's like, right, you lot, you're all deleted, you're all culled, while everything over here carries on. A really interesting case of Director AI is in Left 4 Dead. Now, Tommy Thompson from the AI and Games YouTube channel, go watch his stuff, it's amazing, goes through a deep analysis of the Director AI in Left 4 Dead. And I think this is really fascinating. So Left 4 Dead, you've got 4 players, and they're fighting zombies. A lot of games are like that. Now, they're very specific on how you should play the game. You should not go off as a lone ranger, leaving your 3 teammates over there. You should stay with them, and the Director AI is going to punish you if you don't do that. So how it does that, okay, it does all these sorts of things, is it makes things harder, okay? And it does that also for the entire game. And it's got a bit of an FSM here. You can see we've got peak, relax, and build up. because we want to keep the tension, but we don't want you to rage quit. So we're relaxing. Oh, everything's a little bit nice. There's hardly any zombies around. We get to rest for 30 seconds. And then, okay, you've had enough rest. You're a little bit relaxed. So we're now going to start building up. So we're moving into that build-up state. So we're now going to start spawning more zombies. We're going to bring in more things for you to shoot and kill. And we'll maintain it there for a little while. And then, if you've got that Lone Ranger, it sends more and more zombies over to them to really target them on their own, to drive them back to their teammates. Now, once you've been doing this for a bit, it's like, ha, 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 you thought that's all I had for you, and it throws loads more. So it's high peak stress. And how it does this is it's monitoring, are you doing ranged attacks? Are you doing melee attacks? How many zombies are you killing per second? And it starts looking at all these data points and then deciding whether you need a bit of a break or whether they really should throw more at you. So I think that's fascinating, how you can really control the experience of the player. The final one now is utility AI. It's very similar to director AI, but this one is looking more on what would be interesting, what would make more sense to run for things like your NPCs. So things like The Sims use this. If you've got 2 action plans coming back for your Sims, if they use GOAP, which they do, in Sims 3 and 4 they use GOAP, it will go, okay, well, what's the player asked them to do, and what's their urgent need? Are they going to pee their pants? We think we should do that. So it has a little look at the context and then makes an informed decision on that. And then Alien Isolation, an amazing game, and they're making a sequel. I'm so excited. It looks at the state of the game and either decides whether to make the xenomorph move more quickly, so animate it faster, it just speeds up the animation to make you more tense, or it winds it off, so it animates a little bit more slowly and you feel like, oh, it's moving a little bit more slowly, it's okay. But then, oh my God, it's speeding up, I'm going to jump in a locker and hold my breath, okay? So it can control the tension in a game. Now, the hybrid systems is a whole load of these systems pulled together. And all of these things can come together. I have FSMs, I have behavior trees, I have the HTN, I have a director AI, and I use utility within my HTN. So you start bringing all of these things in together and layering it up. And then that makes it really, really, really fun. So, as promised, I have these resources for you. Grab that, photograph it, whatever. There's a whole list of things for you to look at. If you don't get it, you can grab me afterwards and get it, okay? And then I have an ask. It's my game, The Third Tourist, hopefully in early access next year. Please wishlist it. I'd be very happy. I am going to do more devlogs as well, so I need to get around to that. If you want to see the dev vlogs, it's November North Games. I haven't done one for a while, but I promise you I will be doing one. And with that, I just want to say thank you. Thank you to our saviour for audio. Thank you for the guys at the back who got the audio gun. And thank you for hanging around till 20 to 7 at night to hear me rabbit on something I'm really passionate about. Phew. Thank you. But your work is not done. I need my pictures. Do not move. Sit back down. Okay, now I'm off the hook for the timeness. Okay, you lot first. I always split it in 2 so I can play you off against each other. I'm hoping you two, because you're in my workshop, are going to be like really leading the roars. I'm putting you lot to shame, okay? Are you ready? Shall we do them first so you get a chance to beat them? Yeah? Yeah? All right, are you ready? Oh, I need to get me in the picture, else it's not a selfie, is it? Okay, you ready? I'm going to count to 3. I want arms, loads of activity. I know it's the end of the day, but come on. 3, 2, 1. Oh my God. I tell you, you lot are going to win. You are going to win. You ready? I think you could just do an extra woo and you'd be there. Okay, 3, 2, 1. Woo! That's how you do it. Jeez. All right, you can leave now. Thank you.